OK. Yeah, so today I'm going to be talking about plane partitions and row motion on these two posets. Thanks to the organizers for giving me the opportunity to speak here. This is joint work with Joe Johnson, who's at KTH. So let me tell you about what these two posets are. So these are examples of the two posets. So the first one is the rectangular poset. So it's just a product of two chains. This is the rectangle R64. And the other poset is the trapezoid T64. You kind of, probably you can just see, you kind of just chop off the bottom triangle bit, and you sort of stick it on the top here. So these are the two posets. And what are we going to care about with respect to these posets? So we're going to be looking at plane partitions. So a plane partition of a given shape P, which are also sometimes called P partitions, is just an order-preserving map from P to the non-negative integers. So you can think of this as you're just labeling the elements of your poset with non-negative integers such that when you go up in the poset, the numbers are weakly increasing. And the height is just going to be the maximum number we use, so that both of these, so this is a plane partition of the rectangle, this is one of the trapezoid, both of them have height 8. I'm going to omit all the lines in the Hasse diagram, but everything's always just going to be less than the thing above and to the left and above and to the right. So hopefully that will be clear. OK, so one question which is very natural to ask is how many plane partitions are there of these two shapes? And there's an interesting theorem, which is due to Proctor from the 1980s, which says that actually these two posets happen to have the same number of plane partitions of every height. And there's a famous theorem due to McMahon counting plane partitions fitting inside a box that gives a product formula for this number. It sort of has this nice form, which is sometimes written like this. And so, why is this true? Well, actually, Proctor's proof is sort of interesting. It uses a certain branching rule from Lie algebra representation theory, kind of a type C, type A branching rule. And in particular, it's not bijective. So he doesn't give a bijective proof that, for instance, takes a plane partition of a rectangle and sends it to a plane partition of a trapezoid. And in fact, he remarks that somehow the question of a combinatorial correspondence for this theorem just seems to be a complete mystery. So it seems quite non-obvious from a combinatorial point of view why these two posets should have the same number of plane partitions of each height. So some work that has been done on this, so some partial progress usually for low heights, so L equals 1 or L equals 2, using various methods. And a bijective proof was found recently due to these four authors, Hamaker, Petrius, Pechenik, and Williams, using a tool from Schubert calculus called K-theoretic jeu de Caen. And they call these two posets doppelgangers because they have sort of this property where you can't tell them apart based on the number of plane partitions of a fixed height. And so let me spoil the game here, which is to tell you what the main result I want to talk about is. So we're going to give a new bijection between plane partitions of a fixed height, and it's going to have some additional nice properties. So the first property is that it's going to extend to a continuous map on the order polytope. So I'll say what I mean by this a little bit more in a bit, but essentially this map given by these other authors is it's a piecewise linear map because it's based on jeu de Caen. You have to kind of compare entries. But somehow the domains of linearity, the map doesn't sort of agree on where they meet. And so you can't really extend it continuously. And so we're going to give a new bijection, which is actually continuous in this sense. The second property is it's going to intertwine with an action which is called row motion, which I'll define in a moment. And in particular, we can use this to show that row motion on this trapezoid has finite order, which I'll again talk about is kind of quite a special property. And then the third property is that it's actually going to be the tropicalization of a birational map. So the map itself on plane partitions is a piecewise linear map, but this map is going to basically be the tropicalization coming from some rational, in fact, birational map. And this birational map is also going to respect kind of a birational version of this row motion map. And this will also imply that birational row motion on the trapezoid has this finite order m plus n. So first, I'm going to talk a little bit about some of the polytope stuff, and then towards the end, I'll get into some of the sort of consequences regarding these rational maps. Okay. So first, we're going to need to talk a little bit about polytopes. So probably many of you are familiar with what the order polytope of a poset is. So it's just the set of labelings of the poset, say with positive real numbers or non-negative real numbers between 0 and 1. And the labels go up when you go up in the poset. And it's easy to see from this definition, a p-partition of height at most L is just a lattice point inside L, the Lth dilation of this order polytope. And so you can think of Proctor's theorem as just telling you that, we have this rectangle and this trapezoid, that they just have the same Erhard polynomial. Because that, again, just counts the number of lattice points in these dilations, and those agree for these two polytopes. Well, how can you show that two polytopes have the same Erhard polynomial? Well, one thing that you can do is you can sort of try to cut one up and sort of move around the pieces and create the other polytope. And one instance in which it's sort of very well known you can do this is not with the order polytope of posets, but with a different polytope called the chain polytope. So the chain polytope of a poset is, again, labelings by non-negative real numbers, but this time the condition is not sort of a weakly increasing condition, but instead it's this condition that the sum of the weights along the labels along any chain has to be at most 1. And there's a well-known result by Stanley in his paper on these two poset polytopes, where he showed that actually for a given poset, the order polytope and the chain polytope have the same Erhard polynomial. And the proof proceeded as follows. So he exhibited this map between them, which he called a transfer map. And this map had a number of nice properties. So it's continuous. It is piecewise linear and unimodular. So by this I mean that so it's piecewise linear. And on each piece, it's given by an integer matrix, and the determinant of that matrix is 1. And of course, it's a bijection. And it maps one of these polytopes to the other. And the map is actually quite simple to write down. So if you have a point in the chain polytope, then you can get a point in the order polytope by sort of summing up along chains that end at that element. And if you start with something in the order polytope, then you can get something in the chain polytope by basically looking at the label where you're at and then subtracting the largest label which it covers. And so just to give an example of this, so here, for instance, are 2 points. I scaled things by 4, so I don't have to deal with fractions. So this is a point in 4 times the chain polytope of this poset, which is sort of like it's not the rectangle or the trapezoid, it's just some other sort of right trapezoid poset. You can see this lies in this 4 times C of P because the maximum, if you look at any maximal chain here, the largest sum that you get is 4, or at most 4, equal to 4 in this case. And so this is in 4 times the chain polytope. Likewise, this one, you'll see we have a labeling. It's just a sort of plain partition here. The height is 4, so this lies in 4 times the order polytope. And so there's a correspondence between these. And so the map in this case, for instance, if I want to know why this entry here is 4, well, what I do is I look at all the chains that start at the bottom and end at this element, and I find the one of maximum weight, the maximum total sum. In this case, it's 4, and so that's why this is 4. If I want to go back, like why is this entry here 1? Well, it's because I look at this 4, and I look at the largest entry that is below it. In this case, it's 3, and I take the difference, 4 minus 3, and I get 1. OK. So that's the correspondence between the chain and order polytope. This is what I just said. But there's sort of one sort of funny thing about this, which is there's kind of another thing you could try to do, right? The reason this sort of works is because you're taking yp and you're subtracting the maximum label, which is below it, and we're in the order polytope, so we know those are all smaller, and so there's going to be some positive or non-negative number. But we could sort of do the dual thing. So we could instead look at all the labels above a given thing. So we have y in our order polytope. We look at all the labels above p. We know their minimum is going to be at least the label at p, and then we can take that difference. And that will give us another label zp, and we collect these together, and we get some labeling z, and you can check that essentially for the dual of the reason that you got a chain polytope in the case for x, z will be a point in the chain polytope for p. And so how are x and z related? Well, the answer is that this is a map which is sometimes called rowmotion. So I added some qualifiers here, but I'm just going to take this as the definition of rowmotion for today. So it's the map where you start with a point x in the chain polytope. You go to the order polytope using Stanley's transfer map y, and then you sort of do the dual transfer map to go back to the chain polytope, and you get this point z. So this is rowmotion. And if you're familiar with rowmotion in some other contexts, one thing to observe is that if x is, for instance, the indicator function for an antichain, so you have ones at the location of an antichain and zeros elsewhere, then when you compute y, what you get is you get the order filter, or the indicator of the order filter generated by A. So you just get ones everywhere above where you had an element of A. And then when you do z, you get the maximal elements of p minus this order filter. Okay, so this might be more familiar if you've seen rowmotion in other contexts. Okay, and just to continue the previous example, so here's the same x and y as before, and now here we have this z, where, for instance, maybe we want to know where this 2 comes from. Well, again, we have this labeling of y, so it comes from, you look at this 2 and you look at the labels above it. In this case, there's just this 4. And the minimum of those, of course, is 4. So we subtract and we get 4 minus 2. But in other cases also, like here, this 2, right? The minimum above it is 2, and so 2 minus 2 gives us this 0 right here. Okay. And so the map, rowmotion is the map that starts with x and gives us z in this way. Okay. One word about rowmotion. So for most posets, rowmotion actually doesn't really behave that nicely. For instance, it doesn't have like a small order. It could just have like a very large, complicated orbits structure. However, it turns out that for some posets, for instance, the rectangle, it has very small order. So for instance, when you have a rectangle m by n, its order is just m plus n. So this, for instance, is one instance. Again, I multiplied things by 4 here. Just to keep them integers, but this is essentially one orbit of rowmotion of size 5 for this 3 by 2 rectangle. And actually, Williams conjectured, sort of based on some of these sort of doppelganger properties, that actually for the trapezoid, you should also have the same order m plus n. And this was kind of proved for a special case. I wrote here the vertices of the chain polytope. This is essentially the same as when you're looking at like plane partitions of height 1 by this group of authors recently. Okay. So I promised you that we would describe a map between sort of labelings of the chain polytope of the trapezoid and the chain polytope of the rectangle. And so let me describe for you what this map is going to be. So we're going to call this map zeta. And the basic building block is going to be rowmotion. So here's a labeling of a trapezoid. This is, I think, is the trapezoid T45. And it's, again, this is in 4 times the chain polytope of T45. The maximum weight chain, I believe, should have weight 4 here. Okay, so what do we do? So the first thing we do is we imagine there's sort of an invisible element here, which we're going to try to sort of shift things down into. And then we look at everything above this element here. So in this case, we get this kind of right trapezoid. So this right trapezoid is the same example that I had on the slide a moment ago. So what we're going to do is we're going to apply rowmotion to the labelings here. Of course, we don't have a label at this element here, but it's going to turn out not to matter what we put here. So I'm just going to imagine there's a 0. In this location. So, and then we have these things which were not in this red region, and we're just going to ignore those for now. So when we compute rowmotion on this on this rectangle, we're going to imagine these are just not here. Okay. So as we did on the last slide, so this is like the x that we had on a slide a moment ago, and then we compute y as we did using the transfer map, and then we compute z, and we're just going to throw out this label that's at the top, which in this case is going to be 0 anyway. Okay. And then we still had this sort of these sort of elements over here, which we haven't done anything with yet. So we're just going to shift those kind of downwards by 1. So we're just going to kind of shift them like that. Okay. And now we have this new labeling, which is not still not the rectangle. So we're going to do this again. So we're going to imagine that we have another element here that we want to shift down into. And then we look at the sort of stuff above it, but we're going to ignore this sort of diagonal here. And then there's still this sort of thing out here that's left over. And then we're going to do row motion on this. Again, we're going to ignore everything in gray and just imagine we have a labeling of this sort of smaller poset. So let me do that. Again, go to the kind of order polytope of this thing, and then you get something like this. And then again, on the outside, we're going to shift everything downwards. So just go like that. And then we'll do it one more time. So this is sort of another intermediate labeling. Then we do it on this guy. And then we'll shift everything down, and now we have a rectangle. Okay. So that is the bijection. And the claim is that this map is a continuous piecewise linear and unimodular map that gives a bijection between dilations of the chain polytopes. And so in particular, this shows that the two chain polytopes have the same Ehrhart polynomial. And I did everything on the chain polytope, but if you want to do it on the order polytope, you just conjugate by the transfer map, and it still works. Okay. So let me say a word a little bit about what we sort of do to prove this. In fact, we do something which is stronger in some sense. We work with the birational version of all of these maps. So we do this by looking at sort of what happens when you detropicalize. So we had all these formulas for transfer maps and so forth that used operations like max and plus. So we're just going to change all the maxes to pluses and all the pluses to multiplication. And so the transfer maps, right, we started with a formula that looks something like this. We're just going to sort of do this instead, right? So this is now going to be on, say, positive labelings of our poset. So instead of using minus here, we're going to use divides. And instead of using max here, we're going to use summation. Okay. Or we had this formula, which was z's in terms of y's. So this is now going to turn into this crazy thing, which is, right, so minimum is like, so minimum of a and b is negative max of negative a and negative b. So that turns into this sort of crazy rational function. And then again, we subtract yp, and we get something like this. And these might look sort of funny. It turns out that you can, if you write them like this, they look a little bit nicer. So. Okay, so let me give you an example of kind of what this map zeta looks like in the birational case. I made it a little smaller so that I wouldn't have to write as much. So this is the trapezoid 3,3, which is actually sort of a triangular shape. So imagine this is our original labeling of a trapezoid 3,3. So what do we do? So we do the same thing. So we look at, we imagine we have sort of a thing which is missing here, and we look at this right trapezoid above. And now we do birational row motion on this right triangle. So that involves this, again, doing this sort of transfer map, but now the birational version of the transfer map and the dual transfer map. So I won't do both steps, but you get something that looks like this. You'll see you have these summations here, which correspond to like this ADF plus ADG. These sort of correspond to various chains that appear in this thing. And then, and we also shifted the C. We shifted the C downwards by 1. And now we look at this smaller right trapezoid, and then we do the same thing. So we do row motion on this, and then you get this even more terrible thing. And so the map is, again, the one that takes the original labeling of the trapezoid to this one. And you'll see that actually the formulas get kind of complicated, but there is something which is nice about this. So if you compute the total weight of all the maximal chains in this labeling, so that is for every maximal chain, you take the product of the entries, and then you add that up over all maximal chains, you'll see here that you actually get something very nice. It's the same as it was for the original trapezoid. So these are the 6 chains that appear in the trapezoid. It's not true that each chain here has a weight corresponding to one of these, so they get sort of cut up in some weird way. But the total sum ends up being the same here. So that's the theorem, namely that this map zeta, it preserves this sum of the product over all chains of this labeling. And this actually implies the piecewise linear result, since if you tropicalize this sort of sum of the weights of these, then you get the maximum of the sum over these chains. And of course, if we know that that is fixed, then that implies that if you were in the chain polytope to begin with, then this is at most 1, and then if it's unchanged, it stays at most 1. So that's what we need. And just a word about the proof. So the main thing that we need to do is we kind of need to relate the x and z that are related by this sort of smaller version of rowmotion. And we have some result that sort of holds for a general kind of skew-shaped poset. And the main idea is that we have this formula for x's in terms of y's, and you can think of this as saying, what is this saying? This is some sum over the things that are covered by p. And so imagine you're trying to multiply together a bunch of these xp. Well, you need to make some choice for each p. You need to choose one of the edges below it. And so that ends up giving you some expression in terms of these kinds of arborescences, where for every element, you need to choose one of the edges which is coming down out of it, and then take some summation over all of these things. So when you have products of these x's, those are related to some summations of arborescences of this form. And then similarly for z's, it's the same thing. The formula is like this, but now it has to do with things covering p. And so then you just similarly get formulas for products of these z's in terms of summations, but now they're over arborescences that look like this. And then you need to relate the weights of these sorts of arborescences with weights of these arborescences. And so then you just do some sort of fancy duality trick, and it turns out that all the weights just get multiplied by some constant amount, and it works out very nicely. So actually, the proof of this doesn't use very sort of intense calculations at all. It's pretty nice, in my opinion. With some more work, so this result is a little bit less nice to do, but you can also show that this map intertwines with birational rowmotion, which is not really clear because even though the map is defined in terms of rowmotion, the rowmotion on the rectangle and the trapezoid, the posets are a lot bigger, and so it's not sort of clear how rowmotion on the smaller poset is going to interact with rowmotion on the bigger poset, but you can actually prove that it interacts with rowmotion. And again, it's a result of Grinberg and Roby that this birational rowmotion on the rectangle has order m plus n. And so it follows that, again, birational rowmotion on the trapezoid will also have order m plus n. Yeah, so that's all I want to say. Thanks.
Do you have any questions?
That was a nice talk. Thank you, Ricky. Have you heard of the idea of combinatorial mutation of polytopes?
Yes.
Recently, various authors have shown that a lot of piecewise linear continuous constructions of this flavor can be realized as sequences of combinatorial mutations, I think for Stanley's transfer map that was shown by Higashitani a couple years ago, and then something similar with the piecewise linear description of RSK. Have you thought about whether your kind of move between the two chain polytopes of the rectangle and trapezoid could be realized as a sequence of combinatorial mutations?
Yeah, so actually it is the case that they are combinatorial mutations. It's usually pretty easy to tell just because, I guess the reason here is because you can describe, there's sort of a toggle description of rowmotion, and each toggle is essentially a very simple combinatorial mutation. So, yeah.
Thanks.
So in your example, you iterated this step 3 times
Yep.
to get from the trapezoid to the rectangle. If you stop in between, do you get a shape which also has the same Earhart polynomial?
That's a good question, so let me just go back here. OK, so the question was about what happens with, for instance, these intermediate shapes. Let me go back to the previous one, actually. Right, so you stop in this intermediate shape. So one thing you'll note here is actually this point does, so again, everything was multiplied by 4. So this thing actually has a chain which has weight 5 or 6 even. So kind of the polytope that the corresponding points line here is not actually the chain polytope of this, but there is a sort of different chain polytope which you can take. So usually when you define the chain polytope, you look at the total weights of all chains in your poset, and you get an inequality for each one. Here, what you have to do is you have to restrict to only certain chains. So if you look at just the chains that either contain this leftmost minimal element or one of these 3 elements on the left-hand side, then you'll see that all of those chains that contain one of those elements, their sum here is at most 4. And so if you define sort of a version of the chain polytope where you only get inequalities from those chains, then that will correspond to this thing that has the same Ehrhart polynomial that you began or ended with. And I should say that also these intermediate polytopes are not necessarily lattice polytopes, so it's even sort of interesting that you get an Ehrhart polynomial at all.
So since the poset polytopes of this trapezoid poset are Ehrhart equivalent to the poset polytopes of the other poset, this would mean that the Hilbert functions of their toric rings are the same as for the Grassmannian, right? Do you know if they,
Yeah, sorry,
do you
I
know
can't
if
exactly
they
hear
appear
you.
as toric degenerations of the Grassmannian?
Sorry. Did you ask about?
The microphone should be on.
Clear to your face.
Okay, so basically for this trapezoid poset, do you know if the toric rings, the toric ideals of these poset polytopes, if they can be realized as degenerations of the Grassmannian? Because
Could you repeat the question, please?
Yeah, so the question was about whether it follows that if you whether you can get toric degenerations of the Grassmannian from these
Yes, exactly.
From these trapezoidal posets because they share this this Ehrhart equivalence. I guess I'm not sure, but it seems plausible.
Okay, but they have the right.
Right. Yeah. So
Hilbert function, right?
because of the agreement on the Ehrhart series.
Okay,
But
thanks.
yeah, I guess I'm not. I don't know
you.
for sure. Yeah.
Okay, so let's save further questions for the lunch break and thank Ricky again.